Hi guys, in this video I will be discussing conservation of energy in classical physics, and I will be showing how that relates to Bernoulli equation, hence showing that Bernoulli equation is simply an energy equation and we might solve a question or two afterwards. So let's get to it. So I'm just going to draw a simple mechanical system. Think of this mechanical system as the track of a roller coaster, or the section of the track of a roller coaster, and then you have the ride here. This is where people get into to ride the roller coaster, and then this is another position of the roller coaster here. Now, the roller coaster has certain quantities, one of which is the total mass of the roller coaster, the initial velocity of the roller coaster. I'll call it V1 because this is position 1. So I will just label this as 1, and this is position 2, right? And then what else does this have? It has a relative height. So let me erase this so I can put the relative height. So it has a relative height from, say, the ground level. So this height I'm going to call H1 or H1, H1. And this height at position 2 I will call H2. Now, the mass is still the same on the right, but then at this position 2, the velocity is V2. So, if there are no external forces acting and we are neglecting friction, so we're assuming, so assumption, that friction is negligible, so approximately 0, and there are no other external forces acting on the system, then we would have that the sum of the energy at position 1 is equal to the sum of energy at position 2. I can. So what kind of energy is acting on the system? We have two, basically. We have both kinetic energy, which is energy due to movement. Like when an object has velocity or is moving, it has kinetic energy, and potential energy, which is as a result of an object being in a field of force. A simple example is an object acting upon by gravity. Gravity is a field of force that gives it potential energy. So kinetic energy plus potential energy at position 1 is equal to kinetic energy plus potential energy at position 2. If we proceed solving by substituting what these energies are, equation or the equation of this energy, we know that kinetic energy is given by 1 over 2, the mass of an object multiplied by the square of the velocity, and then the potential energy, PE, in this case it is potential due to gravity, is the weight of the object times the height. So mass times acceleration due to gravity multiplied by height. So we can simply use these two to and substitute into the energy equation. So we'll have 1 divided by 2 mv1 square, right, plus mgh1 is equal to 1 over 2 mv2 square plus mgh2, right? So this simply the conservation of energy of the system is saying that the energy, the sum of energy at position 1 or any other position is equal to the sum of energy at any other position along the whole system. We can simply put it in this form without even specifying the position. So what that means is that at any given position I, the kinetic energy plus the potential energy, let me put the actual equation. So I have mghi, where I is any position, The sum of these two is a constant. So that's just what this means. Now, this we assume that there isn't any force acting. What if there was an external force? So let's assume there's an external force at position 1. The external force, I will call it F1. And then an external force at position 2 on the cap, I will call that F2. So now in this case, we have to put into consideration the work done by that force. So we know that work done is equal to the force doing the work times the distance displayed, the object is displayed by that force. So force times distance. So let's consider an infinitesimally small distance, just to keep, or just to give account of the work done. So let's call this delta x1. And then here I do the same thing. It doesn't matter where I put it. So this force caused a displacement delta x2. So in this case, the equation we got, and I'm gonna call this equation say 1. Now equation 1 isn't complete because I'm not putting into account the work done by the force. Now, putting the work done into consideration, then we're going to have sum of the energy at any position I plus the sum of the energy will be sum of kinetic energy and potential energy hi, then plus that work done, and I'm just gonna call it fi, and that would just have delta xi will give you a constant. What that means is that if you have two positions in consideration, then you have position 1, which is 1 over 2 mv1 squared plus mgh1 plus f1 delta x1 must be equal to 1 over 2 mv2 squared plus mgh2 plus f2 delta x2. So what I just sort of recited is this, but by adding the portion of the work done, right? That's it. So this is going to give you the final equation for this system with the assumption that there's an external force doing work. So how does this relate to Bernoulli, right? Now we're going to show that. I'm going to wipe everything, move some things around just to create more space. I mean, we know the original equation, so so let's wipe everything that we don't necessarily need. Okay, so all these are gone, and then I will have to change the system a bit. So let's assume the system is different. So I'm just gonna wipe everything. I can always draw it again. So let's consider a different kind of system, and I'm gonna sketch it here. So similar to what I drew initially, but now it is not a track. It is like a pipe, right? A pipe in which some fluid is flowing in and flowing out. So now we have two sections, section 1 and section 2. So I'm just going to call this 1 and 2. So let's see how we can use the same equation that we had, which is 1 over 2 mvi squared plus mghi plus the work done by the force, external force, delta xi is a constant. So this is the equation we had from classical physics. We're going to use, again, we have the same representation we had previously. So we have the height from the center of this tubing or pipe. I'll call this H1, not HI, H1. So H, let me use a different color. So HI, I keep using HI. Just give me so, okay. So the height from the center of this tubing at position 1, I'll call it H1, 1, not I. And I mean, we have pressure, right? Or we have force. We pretend I still force. Here I have H2, H2. Now, in this case, we're making some assumption. We're assuming that the fluid flowing through, when you talk about fluid, there are certain attributes or quantities you care about. The two most important as related to this is when you're talking about fluids, you care about two things: pressure and what? Density. So these are the two quantities you care about. So we use P for pressure, rho for density. The assumption we're making for this question, or sorry, this system, is that the density is a constant. What that means is that the fluid flowing is incompressible. That means for a given volume of the fluid at any position within the pipe, the volume is constant. It cannot be compressed by, increasing the pressure or otherwise. So that is the most important assumption, and we're assuming that the flow is uniform. So going back to position 1, we have V1 also as an attribute, V2 at position 2. This pipe has a cross-sectional area at position 1, A1, and a cross-sectional area at position 2, A2. So let's go back to these equations or the properties we care about. Let's start with density. What is density? Density is mass divided by volume. Every time I write volume, I'm going to write VOL. Now, volume is always a function of some cross-sectional area times some displacement or height. Height doesn't mean it's vertical, it could be horizontal. So let me explain what I mean by that. If you have a pipe like this, and you're considering between these two sections, the volume of fluids between these two sections, then the volume VOL is what? That cross-sectional area of the pipe times this displacement, dx. So when I say area times height, I just mean that displacement. So I'm just going to use dx for the sake of this problem, right? So density is always mass divided by volume, and volume is cross-sectional area times that displacement, delta. Okay, let me use the same color. I'm using delta x. Okay, so let's use this to, because we don't really, when we're talking about fluids, we don't care about mass, we care about density. And then we don't care really about force, we care about pressure. And that's why I stated them. So let's see how we can replace mass in the above equation, highlighted in green. We're going to replace the mass with density equivalent. So wherever you see mass, you replace with density, and wherever you see force, you replace with pressure. Pressure, density. Okay, so from this equation below, I can solve for the mass. Mass will be density area delta x, the displacement. Let's just highlight this. And I will do similar for pressure, right? I'm trying to find an equivalence in terms of for the force, right? That would replace, in pressure that would replace the force. So so we know that pressure is equal to force divided by the area area in which the force acts, right? So we can simply make force the subject. Force is equal to pressure times area. So I can also highlight that in red. So in place of force, we're going to be substituting pressure times area. And then in place of mass, I'm going to be substituting density area times delta X. So I'm just going to do it underneath here. Let's erase this portion here. So bringing this equation down, or I'm going to move the assumptions down here. I guess that's better. So I would have more room. So this assumption, bring it down here, right? And then the two important equations that were circled or highlighted in red, I'm going to bring it down there to create room for myself. Okay. So put it here. Now I can erase this because okay, so starting from this equation above, from the classical energy equation we had, so anywhere I see mass, I'm going to replace it with rho A delta X. So I have 1 divided by 2 rho A I delta X I, and then that's just the mass, so I still have the velocity VI squared, right? And then same thing plus rho A I delta X I H I, right? And then instead of Fi, I'll have Pi AI delta Xi is original. So this will be equal to a constant. Equal to a constant. Is that clear? Now, we're going to do some simplification. If you look through, we can divide through by AI delta Xi. So if I divide all through by AI delta Xi, because all those are constant, right? For a particular section, the product of AI delta Xi is the volume. Now, the volume at that particular section, be it section 1, section 2, or whatever, is a constant. So I can divide all through and divide both the left-hand side and the right-hand side. So 1 divided by 2 rho VI squared, because I'm dividing by AI Xi, delta Xi rather, plus rho, oh, I think I forgot to put the G here. There's a G here. So rho HIG, gravity, right? And then plus Pi is equal to K divided by AI delta Xi. But this whole right hand side is a constant because area at that particular position, delta Xi at that particular position is a constant. So I can just simply call it constant K. I can just call this a constant instead of writing it in that form. So it's a constant. I can use C or another constant. So this is your almighty Bernoulli equation. This is Bernoulli equation. And if I was going to expand it to give account to those two positions or two sections in question, then I'm going to draw it out. So I'm going to write it out in full to represent, to show both aspects, right? Both an aspect of the equation representing section 1 and an aspect of the equation representing section 2. So this is your Bernoulli equation, and we found it from the classical energy equation that we have in classical physics, rather, and so it's pretty much the same. So let's try and use this to solve a question. And I'm just gonna erase a couple of things and then move the equation up. Okay. So let's see if I can write the equation in full. So we have 1 divided by 2 rho V1 squared plus rho H1G plus P1, pressure at 1, is equal to 1 divided by 2 rho V2 squared plus rho H2G plus P2. So this is the full Bernoulli equation equating the energy of, well, it's equating the pressure because we've simplified it. It's no longer, the individual quantities are no longer a representation of energy, but of a representation of pressure. So let's see if we can find a question, a sort of a simple question that we can just use to demonstrate. So if we have a question that requires us to find, so I'm just going to sketch this question I found. So let's erase some stuff and try an example to see how we use this equation. Okay, so example exercise. So I'm going to sketch it and then we'll solve it. So we have a system that looks like this. I'll try and do a good job at sketching it, but don't make it too high. Okay, so we have a system that looks like this, right? So we have position or section 1, we have section 2 here, and we have section 3 here, and I'll use red to denote the sections. Now at section 1 we were given the area A1 is equal to 3 meters squared, and P1 is 300 kPascal, kilopascal. Pascal is just Newton per meter squared rather. And then the height here, the height here was given as 20 meters. Now section 2, we have A2, 3 meters squared, and section 1 also have velocity V1 as 10 meters per second, and then section 3, A3, is given as 6 meters squared. So the question says we should find the velocity at section 2 and 3 and also find the pressure at those sections. So the first thing we need to know is the fundamental assumption that was made, and the assumption is that it is incompressible. What that means is that density is a constant. Another way of interpreting it is that volume, a given volume is a constant, right? So volume is a constant. What that means in essence is that area times area times delta x is a constant, but we don't have delta x. What we have is delta x divided by t, which is flow rate, velocity, right? The rate at which, it's not flow rate rather, it's velocity. But what that means is that we can say area times the velocity is a constant. So because if the volume at a given a specific section is constant, the volume of fluid or water flowing at that section is the same as the volume of water flowing in another section, because the fluid is incompressible. So what that means is A1 V1 is equal to A2 V2 is equal to A3 V3. So we can use this equation to find the velocities, right, at each of the sections we're interested in. So because we have A1, so I can say A1 times V1, velocity 1, is equal to A2 times V2. So I can simply make V2 subject, which is A1 divided by divided by A2 rather, A2 times V1, right? And this will give me A1 is 3, A2 is also 3, multiplied by V1 10, which will also give me 10 meters per second squared. 10 meters per second squared. Per second, not second squared, right? I'm sorry about that. Similarly, V3 is A1, A3 V1. So we're just doing the same things, but considering both A1, or section 1 and section, so I'm just going to write section 1 and section 3. A1 V1 is equal to A3 V3. This will give me this, and this will be 3 divided by 6 times 10. And this will give me what? 5 meters per second. You see? So we've been able to find the velocities at section section 2, V2, as also 10 meters per second, and at section 3, which is V3, 5 meters per second. So we've been able to solve that. What we now have left is the pressure. So this is where we now use Bernoulli, right? I'm going to use the interesting Bernoulli equation. So just take all this part away because I don't need it. And yeah. So now Bernoulli, let's start with two sections at the same time. We always equate two sections. So, and I believe it is water. Oh yeah, yeah, it is water. It was stated to be water. So the density is 1,000 kg per meter cube. Yeah, let me see. And I believe it's water, so the pressure, the density is 1,000 kg per meter cube. So let's see. So we have 1 divided by 2 rho V1 squared plus H1G is equal to 1. Okay, yeah, I missed the pressure. Plus P1 will give me 1 divided by 2 rho V2 squared plus rho H2G, right? Let me just remove this area from here so I have more room. And then plus P2. And P2 is the quantity of interest. Remember that these two quantities on both sides are identical. Remember that since V1, remember that density 1 is equal to density 2. Density is a constant, so it's not a question of density 1 or density 2. So remember that V1 is equal to V2. So these two quantities are identical. So now we have 1,000, which is density. Height 1 is 20. Gravity, I'm just going to use 10, is 9.8. Plus 300 kilo, which is times 10 to the third, times 10 to the third. And then equal to the height at position 2 is 0 because that's the datum, the reference point. So this is 0 plus P2. So now I can simply solve for P2, right? P2 is, I guess I should use 9.8 rather than, so this is 9.8 gravity, acceleration due to gravity. So when I solve this, let's see what this will give me. So we have, so this gives me 496 kilopascal. Now the last one, I will use the same Bernoulli equation, but I'm now going to equate section 1 and 3. I can actually do section 2 and 3. It doesn't matter. You can do it any way you want to do it. So I'm still just going to stick with section, or let's do section 2 and 3 because they have the same height level. So you see the height quantities can be cancelled out. So let's do section 2 and 3. That makes the question simpler. So we have for P3, we're going to do section 2, which will give me 1 divided by 2 rho V2 squared plus rho H2G plus P, hold on, I need to, G plus P2 will give me 1 divided by 2 rho V3 squared plus rho H3G plus P3. Now remember that H2 is equal to H3. So this quantity cancels this quantity. So now I can just make P3 subject. So let's make P3 subject. P3 will be equal to P2 plus 1 divided by 2 rho V2 squared minus V3 squared. So yeah, let's substitute the quantities. So here would this will give us 496 times 10 to the third plus 1 divided by 2. Density is 1000 water. That's V2 is 10, so 10 to 10 squared minus V3 is 5, so 5 squared. So let's simplify this and see what it gives us. And this gives us P3 is equal to 533.5 kilopascal. So if we had solved this question or this portion of the question using section 1 and 3, it would have given us exactly the same result. It doesn't really matter which section you decide to use, you will arrive at the same result. Thank you so much for watching this video. Have a good weekend.